I would like to introduce our next speaker of the day, the one and only James Britton. He's a former toy designer. He's currently a YouTube maker with over 1 million followers in general robotics, electrical and mechanical engineer. He's a fan of doing it yourself and innovating by trial and error. Today, he'll be talking on engineering for YouTube content creation. And I must add that my favorite video is the one that you broke the Guinness World Record.
Oh, yeah.
Yes, with the largest 3D
printer.
printer.
Someone's beaten that now with one twice as big.
No way.
Yeah. I guess anyone watching doesn't know what we're talking about. It's not part of this presentation. I did the tallest 3D printed sculpture of a human in the world, which was 11 foot 10. About 50 kilograms of 3D printing. It was me, double life size. Someone's done one twice as big now.
Oh, wow. You have to do it again then. Anyway, please talk to us about YouTube content creation.
All right, thanks. So yeah, I was a bit surprised to be asked to speak at a software developing conference because I'm not a very good software developer. Basically, it's engineering for content is the title because I hack around to make. Basically, my product is the video, right? I don't do any product that's ever sold, so it doesn't really matter how it works as long as it looks good on video. So basically, yeah, I just build it for clicks. Yeah, so as you mentioned, 1.1 million subscribers, 130 million views on the channel in total. That should be higher, and I'm going to talk about that in a moment. But what does it all mean? I mean, those numbers are quite high, but basically those are a symptom of me having just made videos for years and years. I've been on YouTube for 15 years, and I've made weekly videos for 8 years and regular videos for 10 years. So I guess it's like anything else. If you keep going long enough, then you can do it. It's like a degree. You put lots of your own money and time in, and you do it, hopefully, and then you hopefully get a career with that, in that subject, and hopefully it's worthwhile doing it to get a higher salary and get some money back. So this is exactly the same. Anyone can be a full-time YouTuber if you carry on and don't give up. The same as you don't give up your career. So yeah. Where does the money come from? Most of it comes from sponsors these days. There is some money from YouTube and patrons and YouTube channel members and all those sorts of fan funding mechanisms. Most of the money comes from sponsors. Some of the biggest sponsors I've worked with have been eBay, Disney, Lego, Paramount, Sony Pictures, LG. They tend to have dedicated videos. I'm going to mention some of those in a moment. I also have every video is sponsored, whatever it is. So pretty much I do what I want, and then we have ads queued up until August at the moment. I have an agent, so where you see the content creator advertising NordVPN or HelloFresh or one of those brands. There's too many to mention there. Raid Shadow Legends, I've done that one. KiwiCo, all of these things, various CAD software, PCB fabs, all of them want their 60-second ad segment. It's much cheaper for them to pay me to do it because I make the ad rather than having to get a production company to make an ad for their company and go and pay for a pre-stream ad, which you skip after 5 seconds anyway. So the content's much more engaging if I do it. And that's why we get those brands coming. So yeah, I have a talent manager and an agent who line up all those contracts for me, basically. And also I have a lot of helpful brands who want to give me stuff to be featured in the video, including Lolsbot 3D printers, Ryobi Tools, who make all those green power tools, Lincoln Electric for welding, 3D Fuel for free 3D printer consumables, which is very good, my CNC machine, various other tools, and Mano Garden and Home Supplies gave me a shed. I'd never heard of them either, but now you have, and that's the point. So, as I said, I've been on YouTube a number of years, and I kind of changed what I did halfway through. So I did start with building pop culture stuff like Iron Man suits. So I did, before I was sort of really serious about making YouTube content, I built an Iron Man suit, and it took me 4 years in the end, from 2010 to 2014. And that was mainly because I stopped for 3 months at a time and didn't get on with it. And I also basically made one suit, and then I made molds and made casts, and then I made another suit out of it, which I finally finished. Halfway through, I got a 3D printer. Most of it was a manual process at the start. So that's kind of a big legacy for me. There were around 50 videos building that Iron Man suit, and another 50 for another suit I did. So after that, I kind of tried to change the channel and do more serious robotics and stuff like that. So I sort of transformed away from pop culture, although I still did quite a lot of robotics and characters from movies. So Star Wars Episode 7 came out when they really relaunched Star Wars this century, with, of course, the character BB-8 from Star Wars Episode 7. So this is my BB-8 that I built, and I made the head a cutaway version, which was the same as the Star Wars Episode 7 visual dictionary. It was functional. I actually did 3 versions, so I kind of saturated YouTube with building BB-8s. There was an event in 2016 at Excel London called Star Wars Celebration Europe. I think they do it every year, apart from through the pandemic. Last year was Anaheim in California, or this year, and I think next year is back in London again. At the 2016 one, they revealed how they made the real BB-8. So in the movie, there were 7 puppets that they control with sticks and various puppeteering rigs. Some were static, some were on motion control rigs. But of course, they had the real BB-8 that was rolled out on Star Wars Celebration the year before, where they rolled it out on stage and everyone thought it was magic. The red carpet droid that they took to all the red carpet events. So the guys on stage here on the left is Oliver and Lee, who were originally R2D2 Builders Club members, which was a fan club. And they got asked to actually go and work on Star Wars Episode 7, building the real R2D2. And the guys on the right are Matt Denson and Josh Lee from Pinewood Creature Effects. So those are the guys who built the real BB-8 that rolled out on stage. And they, at that event in 2016, revealed how they did it, and they showed the internals for it. So at that event, though, I had my BB-8 actually functioning. So that was the only one that actually worked at that event. So I was pretty happy that I had it working. And this is my BB-8. So I didn't have quite the budget that Pinewood had. They had sort of a lot more money than me, being on a Star Wars production. My main motors cost £2 each, and they were basically windscreen wiper motors that I got off eBay. And there's a big piece of lead in the bottom. So it is actively stable. It's got an inertial measurement unit, which it's trying desperately to keep itself upright. It's a 6-axis machine, and it's basically reading the angle it's at and adjusting the motor speeds and positions about 50 times a second to try and stay upright. So it can rotate on the spot, and it can drive forwards and backwards and lean sideways to steer. And it's effectively running on what would be a virtual axle. And then the head inside is on another lever that moves in another 3 axes. So that's my BB-8. After that, I moved on to some other more serious robotics. So I tend to do these themes on projects and then thrash them until I've done them as much as I can. So I did 3 or 4 BB-8s. I'll mention the 4th one in a moment. And I also did a lot of robot dog projects. So this is Open Dog 2, and I'm going to talk about that some more in a moment. I also spent a year in my spare time learning ROS, the Robot Operating System, which is an open source framework. And this is one of the robots I built. I did all the hardware, all the microcontroller code to read the wheel encoders and work out the pose of the robot, and worked out how to send those messages as ROS topics and how to use the navigation stack. So it can drive around. It's got a LiDAR on the front, and it can do mapping, and it can do navigation. So this is just running ROS. I didn't actually write much software apart from the microcontroller code, but trying to configure ROS, there's a lot of documentation out there and a lot of different versions. So I ended up buying another ROS robot and looking at various examples. But nonetheless, it was me trying to get away from dressing up as Iron Man. I mean, ultimately, I don't want to dress up as Iron Man till I'm 65 and I'm retired. I mean, Robert Downey Jr. has done all right, but I thought I'd move on to some more serious stuff that I was capable of. In 2020, I pretty much didn't do any pop culture, well, apart from Tickle Me Elmo, who's peering over my shoulder. Most of it was serious robotics, so things like force-controlled elastic tendons. The top left is a dynamically balancing strand beast, various other projects. And this is quite relevant in trying to transform the channel, and I'm going to talk a bit more about that in a moment. The only reason I would do pop culture is if a big brand came along and said, we need a droid from Star Wars, please. So this is Colin Furze, who's got, I think, 11 million subscribers now, who builds crazy machines and stuff with lots of fire in. eBay asked us to do a Star Wars promo, and they licensed Star Wars Episode 8 from Disney. So I built another droid, which was BB-9E, which was like the bad BB-8 that's in Star Wars Episode 8. And Colin, being Colin, built a gigantic TIE fighter, which is behind us, out of steel. And that's Kylo Ren's TIE silencer. It didn't fly, but it would have been cool if it did. Anyway, it's a big production with a catering truck and 4 camera guys and a drone operator and health and safety and the CEO of eBay UK and Disney licensing on site. Some kids, they surprised some kids basically. Oh, official Disney stormtroopers, the whole thing. There's quite a good, it was a Christmas video. It was quite a good feel. Then it happens again for Marvel Infinity War. So here's me and Colin again with a box. And then inside the box was a giant Hulkbuster that broke out with pneumatic punching fist. My job was designing the cosmetics to make it look like that. It all had to be rolled out of steel, which can only be rolled in one axis. At least that's all Colin could do. And it still had to be approved by Marvel in the US. So I had to do all the CAD for that and work out how to unfold it onto flat sheets. And I 3D printed the helmet and did all the electronics and control, which had to be risk assessed because it had fire coming out of it, which meant it all had to be operated on a 30-meter cable and no one was allowed near it. Then Paramount asked me to build Bumblebee, the real Transformer. This one I did on my own, but I had to employ someone to help me, and we built the car as well. So this is a life-size Beetle replica. Yeah, here it is half transformed in a gazebo in my garden. And here is the thing transformed. And we basically set up a shoot in a garage where some customers came in for a free tyre check. And then we transformed this thing in front of them. Most of the British public are really bad at reactions. There was one guy who saved the day who was like a bit crazy. If it had been in America, it would have been fine. So some parents brought their kids in as well, and then they tried to interview them afterwards, sort of like, was it exciting? Yes. What did you think of it? Very nice. So anyway, the video was okay in the end. Then we shot our own video pranking a fake traffic warden, which is quite good. You can check that out in my channel. But most of the time, I tried to do serious robotics and not pop culture unless someone had a budget, basically. So on that note, I'm going to tell you why I deleted 100 million views from my YouTube channel. So you'd think videos with tens of millions of views on are a good thing. But I kind of changed what I did. So the problem I had was what some people described as a good problem to have. So basically, the video on the left is a video that's a 4-minute summary of my 54 video playlist of building an Iron Man suit. And the video on the right is another video I did about building the Hulkbuster suit, which is another Hulkbuster that I could wear. That one's got 9 million views on it. And there were several other videos with multiple millions of views on, which totaled about 100 million views. That video on the left was published in 2014, but still by 2020, it was doing 1 million views a month still, which is practically unheard of for a video 6 years old. And then there was a massive spike, and on one day in September, it did 1 million views in a day. And it did about, 7.8 million in that month. So that sounds great. The problem is, when you watch a video on YouTube, YouTube keeps recommending content from that channel, regardless of whether you subscribe. On the front page of YouTube, when you go on youtube.com, you see all the videos. You'll see them from other videos you randomly watched that were recommended, and on the sidebar when you watch a video. So what's happening was 1 million people a day maybe watching this video, watching a viral video of an Iron Man suit getting built in 4 minutes, are then getting recommended serious robotics content about ROS topics and all sorts of stuff about coding. And they either didn't click on it, or if they did click on it, they wouldn't watch very much of it. Click-through percentage and retention percentage are how YouTube rate videos. So what happened was I found that basically the end of 2020 was a disaster, and all my videos nosedived. So the average view went down to like 30,000 views on a video. I still had over 500,000 subscribers, probably 600k by then. So I removed those videos completely and marked them unlisted or private, which took them away. And slowly, by the start of 2021, I was able to push my view count up to more than it had ever been, basically up to sort of over 100,000 views on average, so 3 to 4 times, purely because people would watch a video and then they get recommended more videos that were the same and they click on it and enjoy it, rather than millions of people getting recommended irrelevant videos. So that's just an interesting, the curse of going viral, I think that's called. So I mentioned at the start that this is engineering for content. My product's the video. So what I really like is open source modules where someone else has done all the hard work. So things like Arduino, which is an open source hardware microcontroller, and a microcontroller is where you write your code in an IDE and you download it with a USB cable. It flashes a chip, and then basically it runs that code loop when you power it up, and it doesn't do anything else. There's no operating system as such. And there's libraries and modules, so you can talk to sensors, talk to motor drivers, read switches, read analog inputs, that sort of thing. The other thing I like is Raspberry Pis and NVIDIA Jetson range, which are all single board computers. So those are computers running Linux and so on. And that's what's in the navigating robot running ROS. There are lots of modules and lots of libraries. The whole Arduino ecosystem is really good because lots of people have made clones of Arduinos, and they've made loads of clones of modules. There's loads of cheap stuff you can get on eBay from China, and there's pretty much always an easy way to interface it. So most of my code is reading from one library, maybe even processing it with another library, and then pumping it out to some other physical module that uses another library. So I don't really have to be very good at software development to make things like balancing robots and transformers that can transform and all that good stuff. I do make physical things, so I do a lot of 3D printing. Thanks to Lolspot, who are my 3D printing sponsor, and 3D Fuel. I do have a CNC machine, which I've recently put back together. It was all dismantled and packed away during the pandemic. So that will cut aluminium and wood, which is quite good. So it's an automated, it's subtractive manufacturing that will go around. It's a bit like a 3D printer, but it cuts material away. So it will cut out metal parts. And also I do quite a lot of welding and metal work. And eventually I'm going to get a laser cutter. So, oops, I've lost my PowerPoint. Yeah, cool. So the next section is really about some projects. I've got two sections now. One is about robot dogs and one is about some other projects. So I built quite a lot of robot dogs, as I mentioned, and I kind of saturated YouTube for robot dog projects. So here's some pictures of, these are basically the thumbnail images from each of the projects. So where it says #13 that's part 13 of the series, which means I think there were 18 videos for that one. Across the top is OpenDog1, which didn't know it was OpenDog1 at the time because it was the first one. Then OpenDog2 and OpenDog3. Along the bottom are two mini dogs I built, and also two test dogs, and there's another test leg. So that's 7 or 8. But where did I go so wrong? Why did I make so many? I mean, I guess Boston Dynamics, we know they made several versions, and I guess they probably have a lot more stuff that hasn't been public. They probably have a place where there's lots of test legs. So I guess 7's not too bad, but I'm kind of one person in my spare room, so. I started with bipedal robots. This is one of my bipedal robots, which is a gonk droid from Star Wars. So that's one of those droids that walks around where they're loading X-Wings in the back, and it's a box with someone's leg sticking out of the back. So I thought I'd make one for real. It's not too bad, actually, for something I 3D printed and made with some Arduinos. I think the motors in this were £10 each. So I thought, 2 legs isn't too hard. 4 legs will be easy, won't it? I'm actually going to play that again because it's quite a good bit of footage. I made another one as well, slightly bigger, with some metal parts in and some better actuators. 2 legs is easy. 4 legs will be even easier. And that's where it started. OpenDog version 1 in brackets. So I just got my CNC machine. I could cut aluminium, so I thought I'll make it really substantial. Let's cut loads of aluminium plates, and there's lots of extrusion in it as well. So all the metal is aluminium, pretty much, apart from the steel ball screws, and all the yellow is 3D printed. Aluminium's a lightweight material. Unless you've got lots of it, then it's not that light. This robot was driven with screw drives and brushless motors, so it's like the screw turns and a nut goes up and down. You can just see the screw drives in some of those pictures there. Those screw drives are steel, and the motors are full of magnets and copper wire. It was a fairly hefty thing. I kind of planned it. So I planned as far as the inverse kinematics. So the previous walking robot didn't do any maths really worth speaking of. It just basically fudged some numbers and tried to add a bit onto its feet, dynamically balancing by measuring the angle. This one I worked out inverse kinematics. And inverse kinematics are where I could position a foot in XYZ Cartesian coordinates, in basically coordinates that are right angles to each other, like the little diagram in the bottom left. And then the complicated geometry is reverse calculated so that I can position that foot in and move it in straight lines, and it works back all of the joint angles. There's 3 joints per leg, one at the elbow, one at the shoulder, and one at what I've called the hip, which is the outward moving motion. And I actually built the remote, did all the electronics, and calculated all the inverse kinematics to check I could do the maths to get to the actuator length on that screw. And then I tested it by moving the CAD, measuring the angles, moving the control stick, and seeing if the results were the same. And then I knew I could build it. So the problem with this one was it was very rigid because of these screw drives, which you can't push back. There's no compliance and there's no springs in it. So it did walk along. But as you can see, it's not Boston Dynamics in any way. It was very heavy as well, and sometimes broke under its own weight. So it could kind of walk. It did the inverse kinematics. It could move the feet between positions. As I pushed the stick further forward, the stride would get bigger, essentially. But obviously you can see it's a rather slow, cumbersome thing. There's some flex in it as well, which isn't very ideal. And there's no compliance. So if a foot hits the ground, it pushes it, and it pushes the whole dog. And that's why it kind of teeters along as it goes. I had to buy a crane to pick it up because I couldn't pick it up anymore. And sometimes the joints broke under its own weight. And I hadn't really planned any further than the inverse kinematics and whether it would physically move where I wanted it to, which was a bit of a mistake, really. But there we go. So then I heard about this thing called quasi-direct drive. And quasi-direct drive is where you've got a low reduction. So you have a powerful motor. Instead of having a screw drive that turns around lots of times to move the nut down, you've got maybe a 1 or 2 stage reduction. So you can push the leg back and you can drive the motor back. So here's my test leg. I eventually made 4 and put them on a dog and hit it with a broom. This is moving between 2 positions, but you can see if I push it, then it will comply because the motor can be pushed backwards. I then did a rather clever thing, which was the motor's got an encoder on so it knows where to position it. So I can look at that encoder, I drive it to one position and then see where it actually gets to. And the difference must be the force that I'm exerting on it. So if I'm pushing it to a position of 20, but it's only getting to 10, it means it's hitting something and it can't go any further. Then I can use the difference of those 2 positions. Well, basically the difference is the force. So in that example, I could say, well, I'm only going to drive it to then 15, which is splitting the difference, which is what's happening now. So when I push it, it complies even more. So then it's effectively force controlled. Excuse me just a moment. Yeah, so I'm just recovering from COVID and I've got hay fever, so I'm just going to drink all this water. So essentially what we've got is a force controlled joint. And then I can move on. And I made another test leg, test dog, in fact. This one has rubbery feet. And I made all the mass really high up, so it's really hard to balance on its own. So without any stability control, it falls over. And now I'm doing the same thing, but I'm using an inertial measurement unit to measure the angle side to side. And as it tips over, I'm firming up one set of legs and softening the other set. And that means it's dynamically controlled and it balances and it works for much longer. That only works with a back drivable mechanism so that we can measure the difference between where it should be and where it is. We could put load cells in the legs and things, but then you'd have to read that fast enough and control the motor speed in a very fast loop in order to make a rigid actuator a virtual spring. With this one, the spring is always a spring, even though there's no springs, because the motor is back drivable and the current is trying to hold it in position, the motor driver applying current. So basically, we've got a very simple mechanism that we can easily write some code to make a dynamic leg. I then moved on to make 2 mini dogs to check I wasn't mad before I made another one and I wasn't going to spend lots of money for no reason. So this is the second version. The picture of the CAD for both of them is on the right there. So this is mini dog 2. An interesting thing happens when you make things smaller, which is that they're not too bothered about being rigid. There is some flex in the legs, but there's no back drivability and there's no springs. But because there's less mass and it moves quicker, it's much more forgiving. And mainly the carpet's a bit squashy, which acts like a spring. And because it's not a two-man lift anymore, it worked okay. And this was really just to check that I could actually make a dog that walked. It does have some stability in it, which is that it moves its feet backwards and forwards to position its mass over its balancing point, but it's pretty rudimentary. So I was quite happy that I'd made a dog that walks. It only just had powerful enough motors to hold itself up. But I really wanted to make one the size of Spot Mini. So I then moved on to OpenDog'22. This one has a low reduction. I use really powerful motors. The sort of shiny pieces in there, there's 6 of them, are the 6 brushless motors, and these are drone motors. And then you can see each one's got a belt reduction, which is a 5-to-1 reduction. So we get 5 times less velocity, which is fine because they're drone motors that are really quick. And we get 5 times more torque. And basically each joint is a 5-to-1 belt reduction, and that's it. Lightweight and really simple. And the immediate answer to this was there was much more agile. Oh, sorry, I didn't realize the video stopped there when I lose focus. Yeah, so this is OpenDog'22, which works okay, right? It looks pretty good. It's relying on its motors being back drivable to make a virtual spring, so any impact of the legs, absorbs the impact. There's no dynamic stability. It's just moving its legs on fixed timers to fixed positions. I mean, the stride gets longer as I push the stick forward, but apart from that, it's all fixed. It's got no intelligence. It's blind, basically. The problem with this one was that the motors with those 5-to-1 reductions, let's just go back to that slide, motors burn up power just standing there, so much that the motors get too hot to touch, and you can smell the enamel burning off the motor windings. Mainly because there's only a 5-to-1 reduction, so that motor's really trying to hold its position. Not really enough torque enough torque at all. So I then wanted to move on to a 10-to-1, but that would make the pulleys twice as big. So it's time for another type of reduction. So I designed this thing called a cycloidal drive. I didn't come up with a concept for this, but I designed it so it could be 3D printed, and it can be 3D printed in PLA, which is basically the most basic 3D printing material anyone's got access to. So this is like a strange wobble that's a reduction. So the piece I'm turning in the middle there is the output, and the piece turning around much quicker in the middle of that is the motor on the back with this cam. So this is a 10-to-1 reduction, and there are 12 of these in the next OpenDog. So to test this and make sure it be robust enough, I did this, which is one of these drives on a wheel. Yes, pushing me on a skateboard for about 3 miles. It's not exactly a speed machine, but it did test robustness of the drive. Still all the parts are PLA. As you've seen, there's a lot of bearings and metal in there, but there's basically off-the-shelf nuts and bolts, and a lot of basically ball bearings, which are those metal parts, which help it run smoothly. There are 12 cycloidal drives in OpenDog'3, which means I think there are 384 bearings, including the ones on the other side of the joint and so on. And as you can see, this is much more robust. So the 5-to-1s in OpenDog'2 were burning up power holding them. This one can run on much less current because it's got twice as much torque. It is heavier. OpenDog'2 was about 22 kilograms. This one was about 30 kilograms, mainly owing to all the extra metal. It's got brushless motor drivers. There's 6 O drives, which are open source, and I tried to make everything as open source as possible. So those are the green boards you can see in the side. There's 6 of those. Each one controls 2 joints. There's 3 joints per leg and 4 legs, which is 12. So 12 cycloidal drives with all those bearings, 12 brushless motors. But yeah, it's a lot more robust than OpenDog'2 could only pretty much carry its weight. This one I can kick, and it's pretty resistant to it. It's still not intelligent, doesn't really have any dynamic control, but its legs are a virtual spring with all that holding power, so it just keeps trying to walk if I try and stop it, and it will clamber over objects and pretty much stay upright. So the one thing I did with the Quasi direct drive was that virtual, or like the force control joint. So reading the difference between where we are and where we should be, and then driving partly to that position to make it much more compliant. I haven't done that with either of these. OpenDog2 didn't have enough power to reduce the power to make it more compliant. It was right on edge, holding itself up, burning up the motors. And the problem with OpenDog3 is it has to walk quite quickly. So the green dots in the middle of the body here, on the right hand side, you can see they're right above the feet, which means the force from the ground is driven right into that shoulder joint, which means basically the legs don't skew outwards. On OpenDog3, they're much closer together, which means I couldn't really bend the feet in anymore to be underneath them because they'd be really close together. So now when force is applied from the ground, or the dog on the ground, it pushes the leg out as per the right hand leg of the left hand dog on the screen at the moment. So that's a real problem, because it means if I walk too slowly, then it does this weird skew because the motor still gets back driven. So I still really need quite fast processing to read the force, even reading the encoder that I've got in the code anyway, because I'm telling it to go to that position and knowing where it is so I can control it. To read that back and still adjust the motor still needs quite a lot faster processing than I have. The main thing that's slowing me down is writing to all the motor drivers over serial, because there's 6 of them. I really need CAN bus to do that. Ideally, what I would need is a different dog structure. And the reason it's structured like this is because the cycloidal drives are right on the pivot point of the leg. So the leg has to be further out to clear on that shoulder motion. Whereas with OpenDog2, there's belt drives, which means the motor isn't in the way because the belt moves the axes some distance apart. So ideally, I need an OpenDog4 with a cycloidal drive with a 10-to-1 reduction, then maybe a further 2-to-1 to a belt to get the joints in the right position, and the legs with the feet underneath the shoulder joint. So that will be the plan for OpenDog4. However, my product is a content. People are pretty bored of seeing my robot dogs, so views aren't what they were. Simpler projects have got better views, so probably won't be an OpenDog4. Right, the next section's about more dynamic robots. I mentioned both with BB-8 and with some of the dogs, they've got inertial measurement units in that measure the angle, and typically that's the sort of thing you have in your phone that knows which way up it is, so it can turn the screen round, or you can play a driving game. It's also what's used in segways and hoverboards and balancing robots. So I've done quite a lot of projects which are balancing robots. This is my Sonic the Hedgehog themed balancing robot, which is about 4 foot tall. It's pretty heavy. Heavier things fall over more slowly, so they're easier to control. Again, it's got brushless motors and O drives, and it uses an Arduino with reading the same inertial measurement unit. The thing about balancing robots that makes them work is something called a PID controller. I didn't write this, there's a library for it, which is really useful. A PID controller is basically some maths that takes the input and changes the characteristics to get the output. And there's 3 terms: proportional, integral, and derivative. Proportional means as the robot leans more, the wheels get faster, which is what we want. And so it drives in that direction. However, that's not enough to actually make it balance. I'll come on to integral in a minute, which is the most important one. The derivative is the tangent of the curve. So if the data is going down, you get a very sharp motion down. It's almost like amplifying it in a straight line. And that will make sharp motions, which help to some extent to catch itself. But the most important one is the integral derivative, the integral term. And the integral is the area under the graph. So this is a clip of a video from someone called Jack Monaco, who built a mechanical integrator. So in the olden days before microcomputers, if you wanted to do some integration, you needed a mechanical device. And what we've got here is an Arduino controlled machine, which is an Omni wheel moving on a turntable. So here we can see the input on the left. If it's 0, the output's 0 because the wheel isn't moving. As the function, if the function is a value, basically, so if the robot's leaning over at a constant angle, the output increases to accelerate. And that's because the area under the graph is always getting bigger because it's the area. And if the input is increasing, then the output increases even more. So basically, with a balancing robot, that means it accelerates to catch itself. We do get overshoot, which is where the derivative is useful to make those short, sharp motions to go and basically compensate. If you turn it up too much, you get lots of vibrations. So all 3 terms need to be tuned. It's a bit like tuning a camera with 3 lenses. so that you get them all exactly right. They could all be in or out of focus, and they all have to be balanced. Typically, we have a high integral and a low derivative and proportional somewhere in the middle. The integral is so important to making a balancing robot, at least one that moves smoothly. So I did quite a few balancing robot projects. And then I got a bit obsessed with one-wheel robots. So we all know, we've seen unicycles and these personal mobility vehicles. You'll find they always have to keep moving in a straight line, like a bicycle, to stay upright side to side, and they balance like a Segway front to back. But I thought I'd build some that stand still on the spot on one wheel, or were capable of it. And I used about 3 different methods for this. The first method was gyroscopes. So everyone's seen a spinning top, right, that stands up. It only does that if it can spin round. If you lock one axis, it won't stand up at all. So gyroscopic procession is when you move a gyroscope in one control axis, then it wants to move in a perpendicular axis. If you've ever held a spinning hard drive that's powered up and tried to move it, it feels like it's really weird. And that's gyroscopic procession, because it's a spinning platter. So, and that's because the thing is spinning and gravity's acting on it, and that causes the force to come out at 90 degrees. So yeah, locking one axis, it'll balance for a bit, but it won't balance for very long before it falls over. However, we can use this gyroscopic procession to our advantage. So here's my first attempt at gyroscopic balancing. So I'm using an inertial measurement unit, which is the blue board in the front, and that's measuring the roll side to side. I'm using a PID controller to move the gyroscope in its control axis, which is in tilt, essentially. And that's exerting a perpendicular force to make it balance in roll. So you'll see some metal attached to one side, and that's to compensate for the servo that's on the other side, which is actually moving that control axis. So this now balances on one side. Without the active balance, it won't work, although lots of people didn't understand why it was so clever. But there we go. That's using that perpendicular force to balance it by reading the angle and compensating and exerting a perpendicular force to the control axis. And this is nothing new. It's been used commercially. This is a thing called the Seakeeper, which is almost exactly the same thing, but not made out of 3D printing. It's a commercial product you can buy for boats. You put it in your boat, and it measures the roll of the boat, and then compensates in tilt in exactly the same way. And then it stops your boat rolling around. I'm not sure how many people use them. It runs in a vacuum, and it's probably pretty power hungry. I guess I don't know if you need a generator or something. I assume it's electric. You probably need an engine to produce the electricity to run it, but it does nonetheless stabilize your boat. There's several videos on YouTube. Apparently they're pretty good. So then it was time to make some wheeled robots. This is the first one, which was 2 inline wheels, which is pretty much the same as the first example. This one's got 2 gyroscopes on each side. They spin in opposite directions and they move in opposite directions. So we still get the same perpendicular force, but we don't get any other weird gyroscopic procession, like a spinning top wants to spin round. It's not so important for this because it's got 2 inline wheels. But if it were a one-wheel robot, then it would want to process if it were one spinning gyroscope, which would be bad. So this one again is using 2 gyroscopes to compensate for the side-to-side roll, and then it balances front to back like a balancing robot, like a Segway or a hoverboard. The only problem with this was the motors on the back of those gyroscopes. When the gyroscopes move, the motor mass gets offset, and then it's like leaning on a Segway and it wants to drive away. But the principle's there. It worked okay. I then investigated another thing which looks similar, but instead of a gyroscope, it's a reaction wheel. So the gyroscope spins constantly, and we use that perpendicular force from the control axis to balance the robot. This uses a reaction wheel, which is spinning in either direction around a center point, and the reaction force pushing it back the other way. So again, I put this on a balancing robot. The front to back wheel is the same as a normal balancing robot or a Segway. And side to side, it's balancing with that reaction wheel to make an equal and opposite force that balances the whole body of the thing. So these are kind of quite experimental videos. They did okay, 100 to 200K. fairly average views, mostly small stuff I tested on my kitchen floor. Remember this one. An Omni wheel is a wheel with little wheels around it typically, which means it can slide sideways and roll in its normal axes. I did a promo for Lego, which was to promote an Iron Man Lego set, and there's one just up above me here as well, which is Lego studs on 9 tiles, and they wanted a machine that would display this art set. So I made this thing that with all these arms with 27 servos in that assembles and deassembles it, and it's got 3 Omni wheels. So using the vector between all 3 wheels and controlling the directions and velocity, we can drive in any direction and rotate, which is pretty special. There are forklift trucks like this. They typically have 4 wheels, but there we go. So I thought maybe I could make a balancing robot that uses an Omni wheel. But obviously what we'd have to do if we're going to make it balance on one wheel is make all of the little wheels motorized. So I came up with this method of translating the motion, so we can put a motor on either side of the wheel with 90-degree twisted belts. So there's 8 little wheels, and there's 8 twisted belts and 8 gears inside and 1 big gear in the middle. And that big gear, when it turns, will turn all of the little wheels. There's quite a lot of alignment here with bearings, but all those wheels are locked together. And if we turn it over, you can see the big gear is turning. So the next thing was to put some pulleys on either side. So if we turn one pulley against the wheel, all the little wheels turn. And of course, if we turn both pulleys, then the whole wheel turns. So we can move front to back, or we can translate sideways. So that seemed to work okay. So the next thing was to put it on a one-wheel balancing robot. So this has got 2 motors. There's one in the back as well with 2 drive belts down to each side. They both turn in the same direction. It goes forward and backwards. And if one is, you add or subtract the sideways motion from the main motion, and it will go this way. And it looks like a funny face. So we've got 2 inertial measurement unit axes for both tilt and roll. And we've got 2 PID controllers running on a microcontroller and a 2-axis brushless motor driver. So it did an okay job of balancing. The problem with this was that those little wheels are slightly tapered because they want to follow the contour of the wheel all the way around the outside so that it's round. And that means that the diameter of that wheel varies from the center of the little wheel to the outside. It gets smaller. That means the circumference is smaller, which means that when it runs sideways, the velocity is sometimes more and sometimes less, depending on the position of the wheel in its main axes. So sometimes it's not quite as good at balancing, depending on where it is front to back. So we could compensate for this by looking at the motor encoder for the front to back axes, and then dynamically changing the side to side output velocity, but I didn't bother doing that. So it kind of works, it proves the principle, and I was fairly happy with that for a 1-week video. So what's next for the channel? I talked about I used to do pop culture stuff, and then I did more serious robotics. Yeah, the plan is to make everything I made in the last year or so, but make it bigger. So I rented a 1,000 square foot of workshop where I can get my welder and my CNC out and all that good stuff. I've had it 2 months. I've done quite a lot of projects there. The most recent one that got published is a wearable reaction wheel. So this is a backpack with a lot of steel on a reaction wheel driven by a brushless motor, which helps me balance. So reaction wheel, the little one, did about 150k on YouTube. This one's done like 450k because it's crazy and people like that sort of thing. So yeah, it helps me balance on a beam. It does actually help me. There's a certain technique to walking because there's not quite enough mass or enough reaction. But if I walk and I push off the reaction like people are helping me each side, then I can walk across fairly confidently. The Omni wheel bicycle. So this is almost a one-wheel balancing device, but only my Omni wheel's passive because I've still got the pedals driving the back wheel to go forwards and backwards. So basically it balances sideways, a bit like a balancing robot. but then I can still ride like a normal bike because the Omni wheel will still slide front and back on its little wheels, which are, I think they're 71mm diameter longboard wheels. There's 16 of them. And so it still rides like a normal bike. And I can stop and turn on the balancing, just about. You'll see a little kick there. That's where the integral kicks in, which goes, well, hey, I need a massive value because that IMU's leaning over. It'll stabilize after a bit, and then the idea is I can spin round on the spot and drive off in another direction. That video did 1.7 million views so far and counting. It was only a few weeks ago. This is another type of Omni wheel, which is a ball-shaped Omni wheel. Now, I didn't invent this concept either. It was Osaka University did a project, and there was a translated video on YouTube. Basically, the wheels, the hemispheres are free rolling, and they roll actively in the other axis. So basically, they're like the little wheels on an Omni wheel that are free rolling, and using a vector of all three at 120 degrees from each other, we can move in any direction. The only caveat with this is that when the hemisphere rolls right onto sort of the peak, you can see there's a red wheel in there, and that's because the hemisphere can't slide anymore because it won't roll unless it's on one of its edges, essentially. So there's a little skateboard wheel, which basically breaks the whole thing because it's really bad at ground clearance. It's not too bad. This is at EMF camp. I was expecting it to just get stuck in the grass. It did pick up quite a lot of weeds, but it worked all right, I think. And there's more projects coming up of a similar nature, basically crazy vehicles. I want to do more one wheel balancing things, a one wheel balancing thing I can ride on, and lots of other projects. As I said, I just build it for clicks. So whatever's more popular, that's what I'll do. And that's exactly 45 minutes. So we're open for questions, I guess.
Hey, so thank you so much for showing your projects and robots. I couldn't even blink. I was watching everything. So I was curious, actually, how did you get into robotics and engineering?
Sorry, I'd muted my laptop halfway through, and I didn't hear anything you just said because it was still muted.
Oh, can you hear me now, though?
I can, yeah. Sorry, there was some background audio on some of my videos that was just I could hear, but you couldn't hear, so I muted it.
Okay,
Yeah, sorry. Go
so
ahead.
I thanked you for showing your projects and robots. That was really interesting, and I was actually curious to know, how did you get into robotics and engineering?
Well, I've always been into making things since I was a child, I guess. So there's an early picture of me with a robot made of a bit of wood and some Meccano and an egg box and some chattering teeth and some ping pong balls. It's about 2004 actually that I, as an adult, I guess, started doing robotics again. So, I mean, the brief history is I did electronic engineering at degree level in the 90s, and I worked in IT for pretty much 15 or something years. I worked in the toy industry as a designer. So I worked at Aon Corporation as a product architect in the IT industry doing data center hosting strategy for EMEA from 2004 to about 2015. In that time, pretty much 3D printing became more accessible. Things like Arduinos and Raspberry Pis and all the open source stuff became more popular. Easy access to stuff. eBay's flooded with stuff from China now. And also YouTube came along. So I started putting videos on YouTube in that time, really. And then at the end of that, I was recruited to work in a toy company to do product design based on what was in the strength of my YouTube channel. But yeah, so I sort of started making content, I guess, before YouTube in 2004, trying to do walking robots and putting them on my website, xrobots.co.uk, mostly failing until we got to the Gonk droid and things that I showed in this video. But yeah, there was another previous 7 attempts at walking robots made of much cheaper, horrible parts and wood and things that I could get in 2004 pretty much before I understood really what I was doing.
Interesting. Thank you. And tell me, what inspired you to get into YouTube? Was it your passion?
Yeah, so I kind of didn't really, I mean, it happened accidentally, I guess. So there's another bit to the story about the Iron Man suit, which was I had a mail order company for a time that sold molding and casting products. So like lumps of clay and silicon for molding and mod rock plaster bandages and stuff for doing model making. And I started putting some videos on YouTube to show what to do with the materials. But then part of that was building an Iron Man suit, and then the videos took off and started making more money on YouTube than I was making in profit by selling the products. So yeah, that's one of the things that got me started. Was kind of all happened in a roundabout way. I didn't really intend. It wasn't like I said, I know I'm going to be a YouTuber instead of going to university or anything like that. It just happened over, I mean, many years. 10 years of making videos. I've only been doing it full time for about 3 years.
Makes sense, makes sense. And tell me one thing, if you had unlimited money, or you were, let's say, financed, what project would you build?
I had this discussion with some other YouTubers at an event, and the answer is getting enough helicopters to steal the White House.
Oh my God. Anyway, thank you for sharing. Thank you for the presentation.